Okay, now we'll go the derivation. Now let's derive the relation for effectiveness of a effectiveness and the NTU. Remember, NTU is actually UA by C min. So effectiveness NTU relationship for a parallel flow heat exchanger. Now let's assume that hot fluid is a minimum fluid. So we will write CH is equal to C min. So the other fluid, that is C will be C max. So now effectiveness will be given by, if hot fluid is a minimum fluid, effectiveness will be given by THI minus THO divided by THI minus TCI. Those who are having still doubts, please go back to the previous slide, lecture on previous slide. I will also be sending you the handwritten derivation as a PDF file to you. Okay. Effectiveness can be written as THI minus THO divided by THI minus TCI. This is a case when CH is a minimum fluid, C min. So Q is equal to what is that? C minimum into THI minus THO. That is equal to C maximum into TCO minus TCI, because CH is C minimum and C is C maximum. So Q is written like this. Or from this we can have a relation C min by C max. C min by C max in this case will be TCO minus TCI divided by THI minus THO. So TCO minus TCI divided by THI minus THO. So we have a relation for effectiveness, we have a relation for C min by C max like this. These relations will be used later when we during the course of derivation of the relation connecting effectiveness and NTU. So please keep these things in mind. So Qmax is equal to C min into THI minus TCI. This is also required, Qmax. So we can write this TCO minus TCI is equal to C min by C max into THI minus THO. So you might wonder why we are writing now itself, because these relations will be useful later. We'll be appreciating anything only if we know why we do so. So you'll come to know why we do so. So TCO minus TCI. If you see any relation something like this, TCO minus TCI or THI minus THO, etc., we should be able to write them in terms of C min by C max, effectiveness, etc. So here, if you have TCO minus TCI, TCO minus TCI is written as C min by C max into THI minus THO. C min by C max into THI minus THO from this equation 2. And that is equal to C min by C max into what is THI minus THO? THI minus THO THI minus THO is equal to epsilon into THI minus TCI. So this THI minus THO will be further written as C min by C max into epsilon into THI minus THO. So epsilon into THI minus THO. So if you see any function like this, we should be able to write this in terms of C min by C max, epsilon, and something like this. Okay. Now we have to go back to a previous relationship which we have used while deriving the LMTD relation. If you want, we can go back to the previous slide, derivation of LMTD for parallel flow heat exchanger. ln of THO minus TCO divided by this relation. So either you have to derive this or you should remember this by heart for parallel flow as well as for counter flow. So you can also take this relation directly from the LMTD derivation. So in the LMTD derivation, D of the next relation will be ln THO minus TCO divided by THI minus TCI is equal to minus UA 1 by CH plus 1 by CC. This relation we should remember. ln THO minus TCO. For parallel flow, this is a relation. ln THO minus TCO. This is logarithm of the temperature difference at the outlet secondant, end to logarithm of the temperature difference secondant divided by first end is equal to minus U into 1 by CH plus 1 by CCA. This relation you should remember by heart. We will use the same relation here. That result, that interim result should, we will use it here. ln THO minus TCO divided by THI minus TCA is equal to minus UA into 1 by CH plus 1 by CC, capital CH plus 1 by CC. So minus UA 1 by CH plus 1 by CC. And we will then make a change. We will take this CH outside. And here we assumed that CH is a minimum fluid. So CH equal to C min. So we will use CH equal to C min and CC equal to C max. So this will be minus UA divided by C min. Minus UA by C min into, so this will become 1 plus CH by CC, that will be C min by C max. So we will always be trying to write relations which will have terms like UA by C min by C max, epsilon, etc. So only these things should be there. What is this? UA by C min is number of transfer units or NTU. So we should always try to get terms like this during the derivation for parallel flow as well as for counter flow. So THO minus TCO divided by THI minus TCO. See, go back. This is logarithm of temperature variation at the outlet by at the inlet is equal to minus NTU into 1 plus C min by C max, or THO minus TCO divided by THI minus TCI is equal to e to the power of, see in the next slide, THO minus TCO divided by THI minus TCI is equal to e to the power of minus UA by C min NTU into 1 plus C min by C max. Now this is a relation with the temperatures. We have to have a relation which doesn't have any term in temperature. So what we do is we try to get this ratio manipulated. So THO minus TCO divided by THI minus TCI. We will do one thing. We will try to write in terms of something like THO. If THO is there, we should have a term with THI. So we want a term THI also here. So what we do? We subtract and add THI in this relation. So THO minus THI plus THI. So it is invariant. Now minus TCO. If I have a term with a minus TCO, then if I have another term with TCI also there, plus TCI also there, then that will also help us write this in terms of the heat. So what we do, since we have a term TCO, we will also introduce another term TCI. I have minus TCO here, so I will have plus TCI here. So since I add this with the TCI, I should also subtract this with the TCI. So instead of the two terms here, we manipulate this the numerator such that there are 6 temperature terms, and we segregate it suitably. So THO minus THI. So I take THO minus THI. This will be of useful term, because once I get either THO minus THI or THI minus THI, CTCI or TCO minus TCI, etc. Now this can be related to THI minus TCI either directly or with the help of epsilon and epsilon C min by C max, etc. That's the sole aim of doing this type of a manipulation. So we will write THO minus THI plus THI minus TC THI minus TCI, this THI and this TCI, THI minus TCI, and minus TCO minus TCI. Why I write this minus is TCO is greater than TCI, so I want a positive quantity inside the bracket. This should also be a positive quantity. So what we do, THI minus THO is equal to, we have hot fluid as a minimum fluid. Hot fluid is a minimum fluid. So this can be connected to THI minus THI as epsilon into effectiveness into THI minus TCI, because THI minus THO divided by THI minus TCI is equal to epsilon. So this will be epsilon with a negative sign, because this is negative. So if you want to have THI minus THO, it should be negative. So minus epsilon into THI minus TCI. See, for those people who are still having doubts, we will use see here THI epsilon is equal to THI minus THO divided by THI minus TCI. So whenever we see THI minus THO, we can write this epsilon into THI minus TCI. And whenever we see TCO minus TCI, we will write that as C min by C max into THI minus THO, and then THO minus THI minus THO will further be written as epsilon into THI minus TCI. So TCO minus TCI will be epsilon into C min by C max into THI minus TCI. So that's why these relations are used here. So THO minus THI will be minus epsilon into THI minus TCI, and this THI minus TCI we will keep it as such. And again TCO minus TCI will also be written in terms of the denominator here, THI minus TCI. So that will be, as I said, minus C min by C max into epsilon into THI minus TCI. Now it is very easy, like we have a THI minus TCI, the first term, second term and third term, which is same as the denominator. So now we can cancel all these THI minus TCI in the numerator and the denominator. Thus we have THI minus TCI divided by THI minus TCI, that will become 1 minus, now epsilon is taken out, so there is an epsilon here and an epsilon here. So once we take this minus epsilon outside, this will become THI minus TCI will get cancelled, 1. So 1 plus, now this epsilon and this is cancelled, taken outside, C min by C max. So now we will have the left side is written as simplified to be 1 minus epsilon into 1 plus C min by C max. It is simplified in the sense that this does not have a temperature term in it, which will have only the effectiveness and ratio of C min by C max. So left side is written like this. LH is equal to 1 minus epsilon into 1 plus C min by C max. What is the right side? E to the power of minus NTU 1 plus C min by C max. E to the power of minus NTU into 1 plus C min by C max. Now we have an epsilon in the left hand side. Epsilon in the left hand side, and along with epsilon we have terms containing C min by C max and NTU. So epsilon is equal to e to the power of minus NTU. Okay, we will take this epsilon to the right side and rearrange. Epsilon term to the right side and this term to the left side. So finally epsilon will be equal to 1 minus e to the power of minus NTU into this thing. 1 yeah. There is a slight confusion. Okay. Now this relation is, there was a slight confusion. Now I clarified it. This becomes 1 minus, from this relation, if you take this minus epsilon into 1 plus C min by C max to the right side, then my epsilon into 1 plus C min by C max is equal to 1 minus e to the power of NTU. So this should be like this. 1 1 minus e to the power of effectiveness is equal to 1 minus e to the power of minus UA by C min, that is NTU into 1 plus C min by C max, whole divided by 1 plus C min by C max. So the same thing, it is written in some books or in some materials, 1 minus e to the power of, instead of NTU they will be writing only N. I think in data book also NTU is written as N. So e to the power of minus N into 1 plus C min by C max is the ratio of heat capacity. So heat capacity ratio, it can be written like this also. I think in your data book this is simply written as capital C only. This relation, so now see this relation, this is a relation connecting epsilon and NTU, effectiveness NTU relation. So this is called a effectiveness NTU relationship for parallel flow heat exchanger. See this equation. You don't have to learn this by heart. You have all the equations in the data book. But the derivation will be asked either as a 10 mark or a 7 mark question for parallel flow as well as for counter flow heat exchangers. So you should be very careful with the derivation. So it's actually just try this derivation once or twice. You can see this. I think it's almost time. Now I'll stop with this derivation in this lecture. The derivation for counterflow heat exchanger will be done in the next lecture.